This week I want to talk about analog digital systems and digital logic gates. And we're going to start out talking about analog systems. The world around us is analog. The sun rises and falls in a smooth, continuous fashion. Temperatures warm and cool, rivers ebb and flow. All these physical phenomena around us, air pressures, light, heat, all change in a smooth, continuous way. And that's what analog systems do. And when you're looking at a system, any system like a monetary system, electrical system, even a system like temperature, we'll say the temperature on the planet Earth, any system that you look at, you're going to have a minimum value that values can reach within that system, and you're going to have a maximum value that values can reach in that system. And the distance between the minimum and the maximum is called the range. And let's take the temperature on the planet Earth. How cold does it get on the planet Earth? I don't really know. Every year I ask students this and they come up with different numbers. I don't think we ever pinpointed it down, but we'll just say minus 50. Somewhere we'll say that on this planet it gets cold, minus 50 degrees. And let's say as hot as it gets on this planet, not sure about that one either, but let's say that it gets up to 150 someplace. So the difference of our minimum of minus 50 degrees and our maximum of 150 degrees is a range of 200. And in an analog system, you go between any two values within that range in a smooth and continuous fashion. So looking at this, we see two diagrams. One shows an analog system and one shows a digital system. And you can see at the bottom is our minimum value and at the top is our maximum. And in this case, the range of these two systems, analog and digital, are the same. They start at the same place, and we're going to say that they go up to the same place. But the difference is in the analog system, it is more like a ramp, where the digital system you can see is more like stairs. So as values change in an analog system, we're going to smoothly go between one point and the next. And while we're doing that, we're touching or going across all the points that lie between those 2 points. Our starting point, our ending point, we have to go through every point that exists in between there, and there's an infinite number. Think about it. If I'm going to start here and go there, but I'm only going to go halfway, and I split that distance in half, I can split that distance in half, and then that distance in half, and I can just keep doing that forever. There's always going to be half the distance left. Although they're getting smaller and smaller, they never get down to zero. So in an analog system, that's the way that values change within that system. But if you look at the digital system, you can see that it doesn't. You go through steps, these discrete individual values that you can't get in between. So if you want to get to a particular point, let's say between, on this diagram, between step 4 and step 5, you take a measurement and it's in between there. In a digital system, you're going to have to settle for the one lower or the one higher because you can't settle for something in between. And the size of those steps have to do with a couple things that we'll talk about. And obviously, if those steps get smaller and smaller, they're going to approach the appearance of a ramp, but they'll never get to exactly a straight line. But if you look at the analog system, I can get in between values anywhere on that line. Because of that, analog systems have the ability to be more precise because I can get onto an infinite number of values, where in the digital system I have to settle on one of those steps or the other. Here's a couple examples. I have an analog thermometer and I have a digital thermometer. So if I'm going to take my temperature, and I take this thermometer and I shake it down and I put it in my mouth, and hopefully it was an oral thermometer, I'm going to see the values, whatever it's going to rise up to, 98.6 or whatever it rises up to, wherever it started from and where it's going to go, it's going to move slowly and continuously in all the points that lie in between. Whereas if I use a digital thermometer, I'm going to see those values change in steps and increments. If it's a 0.1 degree, 0.2 degrees, a half degree, don't know. That's a feature of the precision of the particular instrument. But the point is, it's not going smoothly through all the points in between. The clock that's shown there is another example. That second hand tends to go around in a smooth, continuous fashion, whereas in a digital clock, we are moving in increments, usually a second. For this particular clock, it's a second. But again, the increments, the steps, the size of those are determined by the precision of the particular instrument. So if analog systems are more precise than digital systems, why do we use digital systems so much? And the answer is because we like to use computers. Computers are powerful devices, tools, and maybe one of the most powerful aspects of a computer is the speed that it's able to do its work. Yes, it can contain large amounts of information, but the speed of processing that information is probably the main benefit of using a computer. For example, modern computer is maybe, let's just say 3.5 gigahertz, operates at a 3.5 gigahertz processor. That means 3.5 billion times per second, 3.5 billion times per second, it's able to process data. Now, if I were going to count as fast as I could, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, if I could actually count to 10 in a second, how long would it take me to count to 3.5 billion? Well, the answer is about 11 years. Counting at frequency of 10 hertz, it would take me about 11 years to count to 3.5 billion. But a computer is able to not only count that much in 1 second, but it can add and multiply. It can process information at that speed. Okay, so we're going to use computers because they're faster, more powerful than us. But computer world, our world's analog, but computer world is digital. And we'll find out why here in a little bit. But the thing is, if I want to get the real world that's analog into the computer's world where it can do its thing, which is digital, then I'm going to have to make a conversion, and that conversion is called, appropriately enough, analog to digital. There's certain aspects of analog to digital conversion that are important in providing accuracy, fidelity, trueness, and a good representation of the real world. For example, let's take a look at this temperature. I see the temperature rising and falling over a couple of days, I guess. And let's say that I want to take measurements so that I can keep a record of what happened during this time frame. So what I'm going to do is I'm going to go out with a thermometer. I'm going to take a temperature and I'm going to write it down. And then maybe a year later, I want to find out what the temperature was on that day. I'm going to go look at that file, and I'm going to take those measurements, put little points on a scale, draw a line between them, and now I'll have a graph of what the temperature did that day. Okay, so let's say in this case, I go out at 6 a.m. in the morning. I take the temperature and it says it's 97 degrees. Let's say, you know what, if I do this once every day, I can get a pretty good representation of a week. So I'm going to go out the next day and do it at 6 a.m. So now I have a 97 degree measurement on that day. And I plot that, I record that, and maybe the next day at 6 a.m. I've got the same temperature. So I record this over the course of a week, we'll say, instead of a day. Let's say we do it for a week. And every day I went out at 6 a.m. and recorded the temperature, and I got the 97 degrees. So a year from now, I get out that piece of paper and I draw a line between all my points, and it looks like it's a straight line at 97 degrees. It looks like, based on the data that I took, it looks as if for that week nothing happened, but it stayed at 97 degrees. So that's not a good representation of the real world. It does not have fidelity or trueness to what was going on because we missed a lot of changes. There were a lot of things that occurred that we didn't observe because we weren't looking. We weren't taking samples. Now, how could we have improved our accuracy? How could we have provided a better representation of what was really going on? Well, I think it's pretty obvious that if we were to have taken more samples, that would have provided a better picture. In other words, even if I had doubled the rate, instead of going out every 24 hours, if I would have doubled my rate of sample taking to every 12 hours, I would have got points that I had missed otherwise. And that, when I connect those points, is going to give me a better representation of what happened that day. Now, if I double the frequency again and take those samples every 6 hours, I get a better representation. And if I double it again and every 3, more often that I take observations, the less likely it is that I'm going to miss something that happened, that I'm not going to be able to capture a change that occurred, and I can record that. So, one of the aspects of analog to digital conversion that's very important is the rate that you take those samples. And that rate that we take the samples is called, wait for it, the sample rate. So the higher the sample rate, the more frequently you're taking those recordings, those measurements, and by the way, that's measured in frequency. If we're doing 10 per second, then that's at 10 hertz, a sample rate of 10 hertz. So keep that in mind. Sample rates measured in hertz. Let's take a look at the sine wave representing a voltage. And you can see that it's rising and falling like the sine waves do. And the blue line represents the real analog world. This is what comes out of a generator. This is also if you're measuring the distance that a pendulum swings. Starting at the midpoint, it swings all the way to one direction, then it comes back and swings all the way to the next direction. If you're looking at an oscillating fan, it's moving back and forth. Analog fashion. And this is the waveform that would represent those distances either in centimeters or volts away from the 0 point. And it shows that I'm taking samples, those red dots along that line. And you can see in this case I have 1, 2, 3, 4, 5, 6, 12 per cycle. So I'm taking, and I don't know what time it is because they didn't measure that out in seconds, but you can see that I'm capturing those points and measuring them. And the more of those that I have, the closer they're going to be together, and the more accurate the representation or the reproduction is going to be when I connect them. So going back to the steps, the idea of steps, if I were to equate part of that step, so you've got the rise over run, you got runners and risers and steps, and the runners are the distance that go along the horizontal axis, and the rise is the lines that go along the vertical axis. And I said as you make those steps smaller, both in rise and run, then you will start to approach a ramp. If those steps are so small, they get smaller and smaller, they get closer and closer to a straight line. As we increase the sample rate, what we're effectively doing is making this part of the step, the run, shorter and shorter because the distance between here and our sample rate, we're cutting down smaller and smaller. That makes this part along the horizontal axis smaller and smaller. Now, what we're doing over here is called quantization level. And in this process, we're decreasing the height, the rise, these steps. In a sample rate, we're dividing up the time axis or the x-axis, the horizontal axis, and with quantization level, we're dividing up this y-axis, the vertical axis. So the smaller we can make these steps, the more accurate reproduction we're going to have when we connect those dots after we've recorded those values. Now, here's the thing. What we're going to do is record these values using digital memory. And the smaller the steps I have, means that I took more samples. And because if I were just sampling here and here and here, each one of those samples takes a certain amount of memory. But if I'm increasing the rate that I'm taking measurements, each one of those measurements have to be recorded in memory. So I'm consuming more memory the higher my sample rate. Also, each one of these values is represented in numbers that have to be stored in memory. So the finer I divide this scale, the more numbers I'm going to have in between here. Each one of those numbers requires a certain amount of memory. So in both ways, the smaller I divide up both the horizontal or the vertical axis, each one of those divisions takes more memory. So with that comes cost. So how much do we need to divide that up? Well, it depends. Sometimes things are changing so slowly that we don't have to capture it. Or they're changing so slightly from one value to the other that we don't need to worry about that either. If I'm wanting to, say, convert the temperature in my room, in my office here, if I want to convert that to digital, it's an analog process that's going on. My temperature in my room is rising and falling a little bit. The heater kicks on, it goes up a little bit, then it cools. If I want to capture those changes and convert it to digital, then I need to take those samples. But how frequently do I have to do that? And how precise do I need that to be? Do I need to measure every second to see if there's been a change in temperature? About every minute? No, I could probably wait and measure every 5 minutes, 10 minutes, 15 minutes. I don't have to have that level of precision that comes with very fast sampling because the changes that are occurring in this room or this process aren't changing rapidly enough where I'm going to miss something. That's not the case with every process. Now, do I have to, going up the vertical scale, what level of precision do I need there? Do I need to divide that up? So I need to record if my temperature changed in my office a half a degree. But 1 degree, probably not. If it changes 5 degrees, then I might just start to notice it, and that might be where I want to put my precision in that scale. Again, I can save money by saving memory if I just sample and quantize the two most important factors in analog to digital conversion. If I can select that rate and level to an appropriate, but still it serves the purpose as far as accuracy to the level that's required in that system. This is showing that I have these sampling pulses. Whatever frequency these pulses are coming at is the sample frequency, and that is those pulses are going to trigger some circuitry that's going to take the measure. You can see on the first pulse, the sample is at 4 volts, the second pulse is at 5, 7, 6, so on and so on. Here we see samples occurring. And there they are listed as such. But those are analog values. I need to convert those to digital. So I have a circuitry here, A to D converter, analog to digital converter. It's taking those numbers and it's converting them to binary numbers, which we'll also learn here in a little bit. This is showing the values of 4, 5, 7, and 6 in binary form. In most cases, the numbers are converted to binary so that computers can work with that. But for us to do something with it, we typically have to convert it back to analog. So at the other end of our process, we've got a D to A converter, digital to analog, where binary information goes in and DC analog voltages come out. Let me give you an example. A music CD, or it's an MP3, but you have your favorite tunes in some sort of digital format. But music's analog, like everything else in the real world. Sound waves are analog. So in order to get an MP3, which is digital, I'm going to have to convert the analog waveforms coming from the instruments and the vocals, somehow convert those to digital information, binary numbers, and store those. And then when I'm ready to reproduce that event, I've seen this event, I've taken measurements throughout the process, I've stored the values, and now I'm going to reproduce those values. So from memory, I'm going to play that MP3. It's got to go because it's by a bunch of binary numbers. That tune is just a bunch of binary numbers, and it goes into the binary input of the D-to-A converter, and it comes out analog. And we can feed that analog, typically an analog voltage. We can send that analog voltage to an amplifier, to a speaker, which is going to take that analog voltage and convert it to analog waveforms, air, and we've reproduced that event. Now, how fast did I have to sample that, and what level of precision? Well, we'll say 16-bit is a minimum, but 64-bit is even 128-bit is not uncommon. So that means the riser part of my steps are pretty short. Now, what about the sample rate? How quickly do we have to take measurements on those sound waves so that when we go to play them back, they sound the same as they did before? Because if we miss things, if we miss changes that are essential for it to sound the same as it was before, we've got to be looking a lot quicker. Things happen in music. You know, the sound range for human hearing is about 20 hertz to 20,000 hertz. So there are changes that are occurring, 20,000 times per second. So we have to sample at least 20,000 times per second. But you know what? That's not even right, because things are happening so quickly that if we sample at 20, we're going to miss things. We're going to miss things that we'll be able to hear. This is called ghosting or aliasing, and it happens with video, it happens with audio, it can happen with any real analog occurrence that we're observing in an event, and we convert it to digital and then spit it back out later as analog. If we didn't sample fast enough, we're going to experience things that didn't really happen. A good example in video is where you're watching a car, and as the car changes speed, it looks as if the wheels are going backwards, even though the car is going forward. This is a result of aliasing, and it has to do with the sample rate, because when we're filming, we're basically taking samples of images. We're taking samples, and if we're not taking those samples fast enough for things that are changing, we'll get things that aren't there. So apparently that wheel is slowing down at a rate faster than we're taking pictures, and because of that, the changes that are occurring look distorted, and we get that effect in that particular case. Here we see the samples being converted from binary to analog. Now, digital signal waveforms typically go between 0 and 5 volts. So what we're looking at right here is what we call a pulse wave. And 0 is represented by low and by 0 volts. And the 5 volts high represents a binary 1. And we talked about true, false, high, low, on, off, those dichotomous either black or white terms that we can use for logic. This is how we represent it in voltage. And with the switch that we see here, when the switch is low and we're grounding, the output is the other side of that switch. If that's low, we're going to get 0. But if we switch up to high, we're going to get 5 volts. Switches. Now, when we talked about oscilloscopes, I mentioned that it's not always good enough to measure a voltage with a meter, because typically a meter measures averages. And if I'm looking at this data stream, I may get an average that's not even representative. That's not going to do me any good. To get an average, it's not going to do me any good. I need to see the pulses, because if I have a problem with the levels of these voltages not being where they're supposed to be, that is represented as bad data. So in this drawing, we can see that this line is that arrow that's drawn there on the vertical axis for the voltage. Everything above 5 volts and above is considered to be on, and everything below that is considered to be off or 0. So if I get a voltage like the 2 volts, and that was supposed to be 5 volts, that was supposed to be a 1, something sent out, instead of sending out 5 volts for a 1, it sent out 2 volts. It's going to get counted as a 0. If that 6 volt one was supposed to be counted as a 0, it's not. It's going to be counted as a 1. So we need to make sure that our systems are operating properly and producing the right voltage for the right binary number. And we need to be able to see that at times because we can't just take an average. So the oscilloscope is useful for that as well. Let's talk about number systems. Here we have what we're familiar with, base 10 or decimal number system, and you see you have a ones column, you have a tens column, you have a hundreds columns, and it goes on and on and on. You already know how that works. And you notice also, and you know this for a fact, that the ones column, if you multiply that by 10, you get the tens column. So the tens column is 10 times more than the ones column, and the hundred is 10 times more than the tens column. And it takes 10 of each of those columns to make one of the next column to the left. And as you go left, you get more and more significant in those digits that are in those columns. Why did we pick base 10 as our number system? And you're probably going to say, because it's so easy. It's so easy because that's the one you learned when you started learning about number systems. If we had learned about another number system instead, then it would have been just as easy as this system. So why did we pick base 10? Because these are digits, right? And they're called digits because of fingers. Because our number system is developed around the fact that we have 10 digits on our hands and feet. So think about this. It's a long time ago. People aren't thinking about numbers yet. And you're looking out there and looks like you might not have as many sheep as you did yesterday. And something maybe is going on, but I can't tell for sure because I don't know anything about numbers. So how am I going to devise a way to keep track of quantities? And it comes to me that I can say, oh, there's a sheep, and I'll hold down a finger, and then there's one. And every time I see a sheep, I lower one of my fingers until I get 10, and now what do? I filled up my hands and I still have sheep to go. So I think about it for a long time. This is a very big puzzle for somebody back then. And I think, oh, I'm going to curl one of my toes and I'll start over again. So now my curled toe represents a tens column, and I can start over with my ones column on the fingers. So base 10 number system came about as we learned how to count and use numbers, measure quantities, and track and record quantities by using our digits. If we had been born without thumbs, we couldn't open jars, and we would have developed a base 8 system, an octal system, and we would have said, oh, we picked base 8 because it's so easy. But computers don't have fingers, and they don't have toes. What do they have? Transistors. And transistors in a computer are either on or off. So I can either have an on or an off. I can't have 10 fingers to represent quantities. So a computer uses a different number system, and all number systems pretty much work the same. You've got in the ones column, you've got that base or that radii number. And the base 10, it's a 10, but the first column, the ones column, is always that number, base number, to the 0 power. And the next one is an exponent up. In our system, it's 10 to the first, 10 to the second, 10 to the third, et cetera, et cetera, et cetera. All number systems work the same. So in a binary, we've got 2, we're going to use 2, and the values doesn't go to 2. The values go from 0 to 1. Those are my 2 values. Just like in base 10, our values go from 0 to 9 before it rolls over to the next column. So we have a base 2. The ones column is always that number to the 0 power, because anything to the 0 power is 1. So the first column is 2 to the 0 power, and 2 to the first power, or any number to the first power, is always itself. And all number systems are designed the same way, with increasing exponents as you go to the columns to the left. In the base 2 system, binary system, just like in base 10, you're being multiplied by that base number as you go across. Now we talk about bits, and bits, the word bit comes from binary digit. And if we were talked about 8 bits being a byte, we'll also mention that 4 bits is called a nibble. So that's where that word comes from. All right, here's a representation of binary columns. You see, starting from the right, you see a ones column, a twos column, a fours column, 8, 16, 32, 64, 128. So that's 1, 2, 3, 4, 5, 6, 7, 8 bits. This is a byte. I've got 8 bits. And I want to represent this quantity. Now in decimal, I would represent that quantity as 197. But in binary, I would represent that same quantity 11000101. It's the same quantity, even though it looks different. So how did we do that? Well, I would say in this number, 197, do I have any 128s? Yes, I do. So I'm going to flip that up to yes. And I've got a 1 here. And that's this one right here. Now I take 128, subtract it from 127, and with that remainder, will 64 go into it? Yes. Subtracting 64 from that, will 32 go into it? No. So I have to leave this down. Will 16 go into it? No. Will 8 go into it? No. Will 4 go into it? Yes. How about 2? No. 1? Yes. So this is represented this way by whether or not these columns will contain the remainder or not. Here's another 8-bit display. They're using LEDs to represent on or off, 1 or 0. So in this case, if I want to convert this to decimal, here's my binary number, 0, 1, 0, 0, 0, 0. 1, 1, 1, 1, 0, 1. Binary number. What's this number represent? What quantity is represented here if we were to convert this to decimal? How do you do that? Are there any 128s? No. Are there any 64s? Yes. So there is 164, and I put it right there. Are there any 32s? No. Are there any 16s? No. Is there an 8? Yes. So I add that 8 to the 64, and I'm going to add 4 to what I have. I'm not going to add any 2s because there's none there, right? And I'm going to add 1, and I'm going to add these together. This value, this quantity represented in binary here, would be translated to our decimal 77. Here we see a 16-bit word made out of 2 8-bit bytes. What I want to point out here is you see on the right they have the first column there, the first bit, listed as LSB. That stands for least significant bit. While on the other end of this, to the left, you see the most significant bit. And this means the same thing here as it does in our number system, our decimal or base 10 number system, and that is that changes in values in the least bit column and towards that end have less effect on the total quantity than if you make changes on the other end of those columns towards the most significant bit. So yeah, clearly if they make a mistake on your paycheck in the least significant bit column, you may not notice it at all. But if they make a mistake of just one difference in the most significant bit, especially if you have 16 columns in your paycheck, you're going to notice that very significantly. So we'll talk about gates. And digital logic gates, we've talked about logic before, so this is nothing new in terms of the concept. But here, instead of using relays and switches to perform the logic that we want, we're going to be using solid-state devices. And we see a representation of the AND gate first, and we know that in an AND gate, you have to have all of your inputs. In this case, we're using switches called A and B. In this particular AND logic circuit, if I have A and B true or high or on, then I get on in my output. So we see representation here. An open switch is what we're saying is a no or a zero or a low, off, false, and a closed switch are the yeses, the ones, or the highs. This is what the schematic symbol looks like for a solid state and logic gate. And inside are transistors that whenever A has power or is high, and when B is high, that causes through this circuitry to provide an output, a 1. So if this is true and this is true, then this is true. But with an AND gate, they both have to be true. This is called a truth table. This is a representation of how this thing works. And I show different possibilities for combination of inputs. So I have two inputs, A and B, and A can be 0 and B can be 0, or A can be 0 and B can be 1, or A can be 1, or they could all be 1. So these are the different possibilities that these inputs could provide. But the way that this logic works is the output provides an output only based on the states of these and what's inside here. So for an AND truth table, the only time we get a 1 is if all inputs, regardless of how many inputs we have, they all have to be 1. This shows a solid state IC or integrated circuit. It's a chip that would fit into a circuit board, and it actually has 4 AND gates in it that you could use in your circuitry. Here is a 3-input AND gate. And instead of using 1s and 0s, they're using L's and H, but we know that L's are 0. Here are the different possibilities. 8 possible combinations. Let me see if I can explain how you would fill out a truth table the easiest way. As far as determining how many different possibilities we're going to have, the way that you do that is you take how many different possibilities of a single output do you have? And the answer is 2. You can either have a 0 or a 1. Now there's 2 possibilities for any given input, but how many inputs do we have? Well, we have 3. So the way you determine how many different possibilities exist is to take the 2 possible states of an input and take it to the power of how many inputs you have. So we would have 2 to the third. 2 to the third possible combinations, which is 8. And that's exactly how we have. Now, what's the easiest way to fill this out, to come up with these different possibilities? The easiest way, if I have 8, is to start in the first column and go halfway down with zeros, or in this case L's, and then do the rest of the column with 1s or H's. Then on the next column, do half as many. So over here I did 4 before I switched. Now I'm just going to do 2 and switch, 2 and switch. And over here I half it again. So I'm going to switch with 1. 1, switch, 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 switch. So if I do it that way, fill it out that way, I get all of the different possibilities that can exist. And we know that with an AND gate, the only time I'm going to get a high is if all 3 of these inputs are high. And that's what's represented here. All right, here we have an application of using an AND gate. And we're checking the states of the inputs at regular intervals. And those are these pretty much every time there's an A. So let's just say that input A is our timing pulses, and we're going to check the state of input B every time I have an A. When I check the first time this first pulse comes, I see that input B is high. Because I have A and B high, the output's going to be high. Second pulse shows it again. So I get another high. But on the third pulse, even though that I have a 1 for my timing, my input B is 0, which takes the output to 0. And then I have a high and a high that gives me a high, high and a high that gives me a high. So this timing reference is comparing or is looking at the state of the B input to make a decision what to do with B. And here's an application. This is showing a fuel injector. It's a solenoid valve, so it's like the paint nozzles that we had in our paint process. And every time I send a pulse to that, which is electrical current, that pulse will cause the coil inside of that, the solenoid coil, to become electromagnetic, and it'll pull up the valve off the seat, and the pressurized fuel that's behind it will be injected into the cylinder or some sort of a mixing chamber. If my computer is sending out timing references, input A, and it's looking at another part of the computer that says, where's the crankshaft, where do I need to do with the fuel? And if the computer is saying, okay, right now, I need fuel, then that's going to go on the output to the injector and cause that injector to come on. Now here's an OR gate. We talked about these as well. In an OR gate, because these are wired in parallel, if A or B is high or true, then we get a true on our output. There's the schematic symbol inside of that, and there's no relays or contacts inside of this. It's all solid state transistors, but it's wired in such a way, the circuitry is such a way that the logic is performed that if A or B has current or voltage on it, voltage appears at the output. The truth table looks like this. Anytime I have a 1 on an input, I have a 1 as an output. Here's a typical application in a car. If A door or B door opens up, then the output dome light comes on. In a timing circuit, I'm comparing A and B, and if either of these are on at any time, my output is on. So in this case, A is on for a long time, so output's on a long time. Here, A's off, but B's on for a short time, so the output's on a short time. The NOT gate, or the inverter gate, simply does what the name implies. It inverts the input at the output. So if the input is true, the output is off. If the input is high, the output is low. Here's the schematic symbol for a NOT or inverter gate. Typically when you see this little bubble, we call this a bubble, this is an inverter, and they also introduce another way to term inputs and outputs. And in this case, we have A and A naught. That line above it means this is A naught, or not A. This is A and this is not A. But we say A naught. And it's just the opposite. So if A is 0, A naught is 1. If A is 1, A naught is 0. And you can see that this pulse becomes inverted by that gate. Combination logic. Sometimes the operation that I want to perform requires more complex logic than just an AND gate or an OR gate, and then I have to start combining some of these gates to get the function that I need, to get the logic performed that's required to solve the problem I'm trying to solve. So in this case, I have an OR gate and I have a Y gate. Here's a representation with using switches, and we can see in either of these cases, because they're the same, that if A or B is closed, it really doesn't matter. We have to have C before we get an output. And we can see here, I've got to have this one and this one before I get this. So no matter what's coming out of here, if this is a 1, this will be a 1 out here. Or if this is a 1, this will be a 1. Doesn't matter. I have a 1 here. I have to have a 1 here to get an output. So these are the two same logic circuits expressed but two different ways. We're not going to worry about Boolean algebra in this course. If you get into programming, if we get into advanced logic systems, you're going to have, this is a way to represent this function. algebraically. And you can solve, the good thing about Boolean algebra is that if you have a very complex problem to solve with logic, you can express that condition, the conditions that you need. In other words, all logic systems provide a specified output based on the input and what you tell this logic system to do with those inputs. So the middle part of this, the logic part, is what you design so that given specific inputs, you get a specified output. And if that problem that you have to resolve using logic is complex, Boolean algebra is a way to express it and to simplify it and get the most simple circuit to perform the function that you want performed. Showing truth tables, well, we know that we're going to have ones all the way down here for this thing to work. And we can express that just like that. All right, revisiting PLCs or PC inputs and outputs, there's some examples here. I have my CPU. It's located in this part of the computer. I've got a USB drive there that can be used for external memory. I have a monitor as an output device. I have a keyboard as an input device. A printer would be an output device. Speakers would be an output device. The modem would work actually as a communication device. It could be both. A mouse is an input device, a scanner is an output, a microphone an input. Here I have an example of an input to a microcomputer. Let's just say that this is the coolant sensor in our car. So we have microprocessors in our automotive systems. These days almost every car has microprocessors, some of them very elaborate. And what I want to do is take an analog variable, temperature of the coolant, and I want to use a temperature sensor to do that. So what I have here is a resistor that, according to the way it's drawn with this arrow going up, we know it's a variable resistor, but this arrow going up means that it varies upward as the temperature varies upward. So as the temperature goes up, so does the resistance of this. All right, so over here, I've got this resistance in series with this resistance. And we know that this voltage, 5 volts, is going to divide proportionally across these two resistors. And so we can say that the proportionality changes as this resistance changes. Or more specifically, we know the voltage across this resistor changes as that resistance changes. So we can just measure the voltage across this resistor, and that translates to changes in temperature. So I know that if I get a, we'll say a 2-volt change in that sensor, that is designed to represent, we'll say 50 degrees. Now, interfacing. Start with a speed sensor. A speed sensor that's going to count pulses. Maybe I have a crankshaft position sensor, and every time that crankshaft makes one revolution, it creates a pulse. And if I count those pulses and time those pulses, then I can relate that to RPM. Or in a lot of cases, as apparently what we're looking at here, I may have a sensor that works something like the crank sensor, but it's in the rear end, the drive axle, the differential. And every time a certain number of revolutions or pulses occur there, it translates into miles. And if I'm comparing those miles, those revolutions to time, I'm timing them, then I know how many revolutions of my axle I have and how many revolutions takes for 1 mile to happen, or how many revolutions happen in 1 mile. I can do all the math with my microprocessor to translate those pulses coming from my speed sensor into miles per hour. Here I'm using a microprocessor to spit out a voltage, to turn on a transistor, and that transistor is going to provide more power than the microprocessor could do on its own to energize a coil, in this case, that's going to close contacts to supply power to that motor. Transmission of data can be either serial transmission, where the data comes out one at a time, or parallel data transmission, where you're sending, in this case, probably 8 bits at once. So obviously, if I need to transmit 8 bits of information, doing it in serial is going to take longer because I've got to do those one at a time. And I can send all 8 of them here in one pulse. But there's drawbacks. This takes a lot more conductors, so it's going to cost more money. So again, you've got that situation where you need to make a call on what's more valuable to your system, what's really needed.